Okay, it's my a great honor and privilege to have been invited to participate in this Petrobras workshop on the role of geophysical technology in the next 25 years, and in particular what are potential game-changing possibilities that ought to be considered within this workshop. So I want to thank Carlos Theodoro and Paolo Cavallo for this invitation. So migration and migration inversion of the ways that we use seismic data, in particular we use primaries to locate structure and identify changes in earth material properties. This is a list of sort of a timeline of how migration went from post-stack time to post-stack depth to pre-stack time to pre-stack depth to RTM. And in each of these stages, the migration method itself is more capable. And at each stage as well, there's a greater demand for subsurface information, and in particular for velocity, to get an accurate depth image. Similarly, in the area of multiple removal, if you look back to the 1970s, 1980s, there were a set of methods that were used: predictive decon, stacking, FK filter, radon, modeling and subtraction of the multiple. Actually modeling the multiple, in particular for water bottom multiple, and subtracting. And from Delphi, the SRME and feedback loop, the latter being for internal multiples. And again, as you trace this evolution of multiple removal capability, the capability increased and there was a commensurate need for greater subsurface information. The issue is that the industry trend, as it moved to deep water and complex and complicated onshore offshore plays, methods that depended on accurate subsurface information bumped up against their assumptions and either became ineffective or would fail. That reality is true for those listed multiple removal methods and migration methods. So what are the challenges? First of all, if you want to know from a very parochial United States of America point of view, what is the evidence that there are challenges, you can go to the Department of the Interior, the Mineral Management Services, and see the success rate of drilling frontier exploration wells in the deepwater Gulf of Mexico, and that rate is roughly 1 in 10. 1 in 10 success rate in drilling frontier wells in the deepwater Gulf of Mexico. That rate has not changed in 30 years. So that's an indication that there are some issues. If 9 out of 10 fail and 1 out of 10 succeed, there are major challenges yet to be addressed. So among challenges are the need for accurate velocity model for depth migration, for current migration methods. Even if you have an accurate velocity model, do you have a most effective method to migrate through that a complex velocity to get a undulating and diffractive reflector imaged? And in addition, are you treating all frequencies with equal effectiveness? So there are challenges even if you had the accurate velocity for actually migrating through it to locate and identify structure. And last but not least, for those who are ambitious enough to want to do amplitude analysis, in addition to structural determination, you need all properties of the subsurface with conventional methods, all velocities, densities, absorption, and so on, in order to perform migration. So this is no small set of challenges. All current velocity analysis methods, common image gather flatness, and then FWI, a misnomer, full wave inversion should be called full wave modeling. It relates to modeling and subtraction of multiples. Used to be looked at as a method which was abandoned, okay? But it is a model matching method. So current methods for finding a velocity are indirect. Common image gather flatness looks for a property that the correct velocity would have, and so-called FWI starts with some modeling equation, tries to match it. So make model matching assumptions. A response to that within the arena of needing a velocity, determining a velocity to be then used for migration, we advocate that people to look at a direct parameter estimation method that derives from the inverse scattering series, which is inversion, not model matching. And that pioneering landmark contribution came from Haiyan Zhang of this group. In terms of after you have an adequate velocity, this group has extended some within conventional migration. There are three imaging principles. Imaging principle called exploding reflector, and then there's imaging principle which says take the reflection data back and the source field forward until the time and space coincidence, which is what we call Claerbout 2, and that's behind all RTM. And then there's Claerbout 3, which is predict the source and receiver experiment at depth and make them coincident and ask for small time. And then Stolt extended that initial Claerbout 3 imaging principle to allow for curved and diffractive structure and yes. And it turns out that Claerbout 3, which is not RTM, is intrinsically superior to RTM in two very important ways. If you have a curved boundary or a diffractive boundary, current RTM, the model of it doesn't accommodate that type of structure, whereas Claerbout 3 does. And in addition, with Stolt's extension, you can not only determine structure of the kind I just mentioned, but you can perform amplitude analysis at that structure, which is curved and diffractive. What we have done recently in this group have extended that Stolt extended Claerbout 3 to allow for heterogeneous media in a way that doesn't compromise low frequency. In other words, Claerbout 3 and Claerbout 2 are very different in terms of how they treat frequencies. Claerbout 2, which is behind all RTM, is a high frequency approximation and does not treat low frequency or lower frequencies with equal effectiveness as high frequency. Claerbout 3 is intrinsically equally effective at all frequency, and that has resolution consequences, which this group has studied. Yang-Li Zhou, Chung Fu, Chao Ma were among those studied and looked at the differences for broadband data that Stolt extended Claerbout 3 would provide compared to RTM. Okay, those are conventional ideas and extensions of them. However, if you're looking for a game-changing method in the area of imaging, locating, identify structure, everything we've said up to now is not going to do that. They're basically taking conventional ideas. Well, we also hear about using multiples. Using multiples, we have to understand what that is. The only thing that gets migrated or migrate inverted is primaries. If you don't have adequate primaries, people can show, you can show, and people have demonstrated that you can get a very approximate image of an unrecorded primary from a multiple. What do you mean by very approximate? It's less than what Claerbout 2, less than what RTM would provide. So, if you're really interested in improved structural determination and amplitude analysis, are serious about it, okay? You have to just bite the bullet and acquire more data. You just have to get, obtain, measure, record more primaries. Because only actual recorded primaries can take you through either Stolt extended Claerbout 3, for the benefits I mentioned a minute ago, or what we're about to show you now, which is direct depth imaging without a velocity model. Direct depth imaging without a velocity model. So here's where that project sits within our tree of topics within this group. This is, we're not going to give a lecture on the inverse scattering series, except to say that this set of equations on this slide 17 here, this one set of equations which represents the inverse scattering series, communicates a very important message. It says, first, it's a direct method. It's the only direct inverse method for a multidimensional Earth. Lasse Amundsen and others have produced direct inverse methods for 1D Earth. The inverse scattering series is the only direct method for a multidimensional Earth. In addition, it has a very special property that every single term in its solution for inversion is achievable directly in terms of data and reference properties, which could be water, and so in the marine case. And that, let me repeat that, every single objective, seismic goal and objective that you can imagine resides within that set of equations, and is achievable, obtainable, computable directly in terms of your data and no subsurface information. Free surface multiples, internal multiples, depth imaging, amplitude analysis, Q compensation without Q. There's a sub-series of this series that Jose Eduardo Lira and Kristin pioneered that takes in, that sub-series of this series takes in data that has suffered absorption and dispersion and outputs data as though it never had absorption and dispersion, and it has no need or interest in knowing the absorptive and dispersive properties. So understanding what this communicates is the beginning of understanding why we search within this set of equations for different subseries for different tasks. If you don't understand that, why would you be looking for an internal multiple attenuator or eliminator within it? You have to understand what it's communicating to begin with. Understanding what it communicates and understanding where that potential resides are two different items. But it communicates that all processes that you can associate with inversion, anything you can imagine that an inverse process which would take in data and output an Earth properties, in data, out properties, anything that you can imagine between taking in data and outputting a description of the subsurface, anything you can imagine is achievable directly and without subsurface information. What does directly mean? Why do we keep harping on directly? Directly, if you need an example, is you can consider the quadratic equation, ax squared plus bx plus c equals 0, and you have that famous formula, minus b plus or minus square root, and so on. That formula says you give me a, b, and c, and I give you the roots. They could be real, they could be repeated, they could be complex, they could be imaginary. It doesn't care, it doesn't search, it doesn't minimize, it outputs the roots. In exactly the same way, the ISS free surface algorithm, pioneered by Paolo Carvalho of Petrobras, when we worked together when he was a student at UFPA, takes in the data and directly predicts free surface multiples and eliminates them at every order. There's no searching, there's no seeking, there's no hoping. It is direct. That's what direct means. Carvalho's free surface algorithm is as direct as the quadratic equation. And then it moved on to Araujo with Ayal locating the internal multiple attenuator, yes? Which in the same way, in comes the data and you predict the internal multiple of any order. And it gives the exact time and approximate amplitude, and then you have Yang Li Zhao, Chao Ma, retrieving from the same inverse scattering series the internal multiple eliminator, yes, without any subsurface information, and it's direct. It tells you exactly what to compute. It's not minimizing anything, it's not searching, there's no weights, and there's no generalized inverse. And there's definitely no model matching. Okay, so we're on to the issue of ISS depth imaging, which in our view is a game changer. This is, there was a whole set of activities, extremely controversial, remains controversial, to do, by the way, ISS internal multiple attenuation was extremely controversial. Mathematicians and physicists all over the world sent us proofs that that was impossible. So, but now everyone, PGS, CGG, Schlumberger, they'll sell you that service, ISS internal multiple attenuator. Okay, so what was intrinsically impossible, in principle impossible, has become conventional and mainstream. From that same exact thinking, that slide 17 derives the capability to do direct depth imaging without subsurface information. A whole set of students within this group, Simon Shaw, Kristin, Jingfang Zhang, Zicheng Wang, and Fang Lu, progressed that set of capabilities to do direct depth imaging without any need for subsurface information. As direct as free surface and internal multiple, its depth. We'll say another word about direct in a minute. So on the left is a model. This is Simon Shaw. On the right is a water speed migration. And then what happens is there's a multiplicative communication between the water speed migration and itself over and over again, just in the same way that you have traces multiplied by themselves in Carvalho, and in the internal multiple attenuator, you have water speed migration of a Stolt extended Claerbout 3 variety in the internal multiple attenuator. That's exactly what gets input here. So this is a water speed migration of the primaries here. And then you're going to see this trace communicate with itself through multiplicative communication, just like in the free surface and internal multiple case. So the movie on the right shows what happens as sums of terms are added. Each term is a multiplicative combination, quadratic, cubic, and so on. There are 67 terms to reach this point. A very important property here that you'll see if we play this movie again. You'll notice that this addition of terms continues shallower, and the deeper one stops. What happens is there's something profound about the word direct. Direct leads to a concept called purposeful perturbation. The inverse scattering series is not a perturbation series, it's purposeful perturbation, but for one reason. Because it's direct inversion, each term in that series has a purpose identified within the task that it's a subseries of. So if you look at the internal multiple attenuator and you give me a data that doesn't have an internal multiple, the integrand becomes 0. In other words, it doesn't just perturb. It decides whether its purpose is called for in your data, and then it acts And how much it acts depends on how big the issue is that it has to deal with within your data at any given location. That's amazing, okay? So when this reflector here needed more help, it kept allowing more entry, more multiplicative combinations. This one didn't need it, it stopped. In other words, automatically, the inverse scattering series for a given task determines, looking at your data, it looks at your data, you don't have to tell it, how many terms you need to achieve a certain purpose. And when it determines that its task is achieved for a given location, it automatically stops. It doesn't allow any further addition of terms. That's purposeful perturbation. That is a consequence, again, of direct. Direct means terms have purposes. They're not searching, they're not matching, they're predicting, they're outputting. Yes? So each term has a reason to be. This is the corresponding pre-stack, and you'll see you'll notice here that this reflector 1D as a function of offset or angle here became flat when it was satisfied. It turns out that the common image gather flatness is a way that we can see that it is satisfied. Okay? Common image gather flatness was developed as an indirect method when people could not find the velocity for depth migration. They said, well, we can't find it. We can't find it, so let's find a property that a migration would satisfy if we had the right velocity, a property. And if you have the right velocity, then different subsets of the data will give you the same depth. So they said, well, let's seek different velocities, such that a common image gather would be flat. The problem there, which none of the common image gather flatness people ever acknowledged, was that you can have the right velocity definitely will satisfy that property, but many wrong velocities will as well. And the more complicated the situation you're in, the more complex situation, the more velocities there are that will satisfy common image gather flatness, including the correct one, but including many that are not. And that's led to an issue. Suddenly we have FWI, without ever acknowledging that FWI, or common image gather flatness, had limits. And so the common image gather flatness for ISS direct depth imaging without a velocity is not a substitute for not having the velocity. It doesn't need the velocity. It's just an indicator that it stopped, that at some point it said it hasn't had enough terms and it doesn't need to have further help. If, however, you have a certain capture of ISS direct imaging terms, and if somewhere in your image you look for different subsets of the data and you have common image gather not flat, it means you need further capture of terms. That's what it means. When it's flat, it's a necessary and sufficient condition that a direct method has reached its purpose at that location in depth. So that couldn't be further different. So this is Feng Liu's famous SALT model. And here's a water speed image. The red indicate the boundaries. You see how far this is from top salt. This is Feng Liu's ISS depth imaging with a certain degree of capture. More terms here than in Simon Shaw's initial capture. Then this is Zicheng Wang's further capture again. This is extremely encouraging. The speed of this, to output this, takes 30% more time than just the Fourier water speed migration. So it's rocket fast. Why? Because each of these pioneers, Simon, Jingfang, Ininin, Fang Lu, Zicheng Wang, have had closed forms for these terms that they're capturing. And these closed forms allow for tremendous speed. This is a fault shadow example. This is a water speed image. This is Fang Lu's result, and this is Zicheng Wang's result. This is a picture of Fang Lu. This is Marmusi, a complicated, multi-dimensional challenge. This is a water speed image. These green, red, blue lines indicate structure, and you're going to see the difference. We'll flip back and forth. So this is these are essentially right on, absolutely no velocity. HOIS plus LE are steps in capture of imaging terms. There are many more terms yet to be brought in, and we'll discuss that in a minute. These are some of different subsets. So this is an amazingly impressive result. No velocity information here. When you get in here, it's encouraging, but not exactly right on, because you have a lot of rapid lateral varying, which is going to require further capture. This is just illustrating that in locations, you see this non-flat CIG in the original water speed, and then in A and B and C, C is into the worst area. C is getting further into this. So after HOIS, after higher order imaging series terms, there is still move out. The common image gather is not flat, meaning it needs more terms in the series to achieve its goal. Okay? So the flatness is, are there enough terms or aren't there? This is all within an acoustic model. Okay? And we'll speak about that. This is Kristin field data. So there, we were looking for viability. New concepts go through stages. First, there's a thought. Something is possible. You capture it in mathematics. You test it on synthetics. You see synthetics with tremendous encouraging results. Then you go to field data to look for viability. Is it possible on field data? After that, there's a big step. Is it going to add value in your toolbox of imaging methods? The state of ISS, direct depth imaging, without subsurface information, is it's viable. It is demonstrated that it is able to perform in not only complex synthetics, but on field data. It has to have further capture and extended to elastic medium to be able to sit in the toolbox as the choice for direct depth imaging under the most complicated circumstances, which are beyond all velocity analysis and migration methods today. Okay. So basically, what's going on in the Kristin is there's, this is data that owned by ExxonMobil, Eni, and Total, and this was joint work with Statoil and Schlumberger, this work. Statoil, Lasse Amundsen, Schlumberger, Ed Kroll. So this is quite a group activity, and these four events represent a water bottom reflection, an internal multiple from the water bottom, and then a sub-water bottom reflection, and then a a third reflection. It turns out that in this case, I won't go into the analysis, there's a paper that we published in 2012 with full detail that I'll send along with this video that delineates this. The water bottom here was only a density change. And how we knew that is the angle dependence of the reflection coefficient at the water bottom. It was independent of angle. So that velocity didn't change there. So it was mud and basically a density change at the water bottom, which gave you sort of C0 and then C0 again, and then C1. Okay, so the third primary is the one we were after imaging, and this is the third primary. Above it are the two earlier primaries that are already accommodated by water speed. This has a move out with water speed. This is ISS depth imaging, flat. Meant it moved, it got deeper, and it was satisfied, meaning that is the depth. So that was, this is what happened. So that means on field data, this ISS depth imaging was able to take a water speed image of something that's gone through C0 and C1 and placed it at the correct depth. And how do you know it's correct? Because the ISS imaging gave you a flat common image gather output, which is a necessary and sufficient condition that ISS depth imaging has achieved its goal. And so that says that it's viable. The job after this is to make it a toolbox. Okay, so this workshop is about game changing capability. I would respectfully suggest the following. If you have a presentation here on any subject, FWI or whatever, and everyone in the room nods, everyone in the room is in agreement, then it's not game changing. It's conventional, it's mainstream, it keeps everyone comfortable. Okay, you could have cosmetic, small changes. You're not going to have a major change in your drill success rate. To have a major change in a drill success rate, you have to have new concepts that will make the majority of people, researchers in particular, research managers as well, uncomfortable. It's just the nature of things. In my history, every single place that I worked, 95% of the researchers and 95% of the research managers opposed everything we ever did. We were fortunate that for the 5% of managers who were enlightened and lead researchers like Andre Romanelli, like Neva Zago, like Ricardo Rosa, like Paolo Siston, that these managers gave us a chance. Gave us a chance when I was a visiting professor at Federal University of Bahia, and I'm grateful for that opportunity. None of what we described here today would have occurred without that opportunity. So an indicator of something being game-changing is the discomfort that most researchers and most research managers will communicate. If they roll their eyes, it means it's new. And if it isn't new and significant, and it doesn't have a chance of matching the disconnect between the challenges we face today and our current capability. In conclusion, as we know, and as Petrobras was directly involved in, the ISS free surface and internal multiple removal had a game-changing impact on the seismic industry. It is not in any doubt that when you have the most complicated, daunting challenges, that's your choice. From the same exact set of equations, the ISS direct depth imaging without a velocity model will have a game-changing impact on structural imaging and amplitude analysis. It is the only candidate that we see today with game-changing capability for structural determination and amplitude analysis. Again, I thank you for this opportunity and privilege to participate in your workshop. Thanks.